Welcome back. So let's continue on the data frames. First, let me ask you a question. Imagine that one of your friends who is a student at ETH, he didn't attend this lecture and he has a semester or she has a semester project. So they want to query the data, right? And they come to you because they need help. They are trying to query a JSON data set. And so they heard about Spark. So they are using Spark RDDs and RDD transformations in order to query their JSON data. So let's say it's a terabyte of JSON. But they have two problems. First, it took them 2 weeks in order to manage to write all the code for their query. And second, it's super slow. Like it take hours to execute. Can you give me 3 pieces of advice that you would give to that friend? So they're querying JSON data with Spark using RDDs, writing PySpark, and it takes them a lot of time and it's slow to execute. How can they address these 2 issues?
One solution is use Spark SQL.
Yes, absolutely. So that's the first piece of advice. They should be using Spark SQL. It's so much easier to use Spark SQL and write SQL rather than write transformations. Actually, you gave 2 answers because Spark SQL also implies that you also recommend that they use data frames because Spark SQL work on data frames. So the first advice is you should use the data frames and not the RDDs. And the second piece of advice is you should write SQL and instead of transformations. So basically, that means that you recommend them to do something like this, right? They read JSON as a data frame and then they write Spark SQL. Okay, that's 2 pieces of advice. The problem is that it's slow. Yes, go ahead.
Use Parquet instead of JSON file.
Perfect. That's exactly the third piece of advice. Use Parquet instead of a JSON file. That's exactly it. So that's what they need to do first. They need to convert their JSON data set to a Parquet data set. Then they write Spark read Parquet with the Parquet data set in there, and then the same SQL. That doesn't change. But then it will be faster because Parquet is much more compact, it's much smaller, and the schema is already there. So yeah, absolutely, absolutely great. That's exactly it. Now, how do you give me 2 ways that they could do this conversion to Parquet? Can you imagine 2 ways of doing it? So there's one that we've seen in an exercise, right? Anybody? How do you practically convert a JSON dataset to Parquet?
Spark read as JSON and write as Parquet.
Yeah, exactly. That's one way to do it. So you do exactly this, Spark read JSON, and then immediately df dot, so an action, it's not going to be take, it's going to be write to file, I don't remember the exact name, but just reading as JSON and writing back to Parquet. The advantage here is Spark will figure out the schema for you. So you don't even need to take care of it. And another way to convert to Parquet if you want to specify a schema. Right, let me just tell you. So it's what we did in the exercises, right? Yeah, go ahead.
JSON.
Yes, exactly. You can use RumbleDB and JSON. So it means that you open with RumbleDB the JSON file. you write your format using the JSON compact form, which is very similar to an object. You validate it, and then you write it back as Parquet. That's another way you can do it. Right? All right, so either with RumbleDB or with Spark. And in many cases, if the schema is easy to guess, Spark is the easy way, because with Spark, you will just 2 lines of code and you can do it. And then I promise to you with Parquet is going to be much faster, because the conversion to Parquet is just once. And once you have done it, then you just go ahead and query directly from Parquet. All right, so that's the good practice. Okay, and I'll come back to RumbleDB, right? Why RumbleDB can be useful for some things. All right, so schema in France, that we saw, the types, so you can read all of these formats. Okay. There is also a way, but here it's more like a remark, so you're aware, but it's I think it's really used maybe in bigger projects, that you can even also create your data frame schemas in Java and even do that as Java classes, and then the Java class will be mapped to the columns of the data frame. So I would say it's a bit advanced, but you can if you want. So in that case, you use again a Java class to denote the types. Okay. So you see, this is why in the first week of the lecture, we spent so much time on brushing up SQL, because it's so important and it is directly useful in order to query data that you have sitting in data frames with just a few lines like that, and with no need to learn new things, because SQL is already something that is known from relational databases. All right. And again, as I said, it's also possible instead of SQL to do manual transformations on data frames. That also exists, but it's a bit more cumbersome to learn. I mean, this is much easier to learn than that. Okay, so the idea is that we have the queries that are using data frames and Spark SQL with the logical plan, and Spark will automatically optimize and silently in the background convert that to a physical query on RDBs. But it does it for you, so you don't have to do it, right? But what happens in the background is that Spark is actually going to create RDBs with a physical transformation, right? So it's really a layer on top that makes it easier for you and exposes the data to you as data frames, while in the background it's using RDBs. So there's a whole paper about that, but basically there's a whole pipeline of optimization that it takes your SQL query on your data frame, and then it's able to infer a lot of things and compute a lot of ways to make it fast, with coming up with physical plans and cost models, looking at 10 different ways of executing it, selecting the one that is likely to be the cheapest and the faster one, and then it generates code and executes the RDBs. But you don't have to worry about that, because this all happens automatically behind the scenes. All you ever see is that your SQL query and the data frame, and this is all the magic stuff that happens in the background once you have done it, right? Okay, so you see that's a Spark SQL dialect that looks very much like SQL. Select from where, group by, having, order by, limit, and so on. So that you all know. There's a few additional constructs though that you don't have in PostgreSQL or in other SQL dialects. There is also here a sort by. So there is order by, that's the SQL order by, and there is a sort by. A sort by basically sorts the data, but only within each partition. Remember that the data frame is spread over the cluster. So you might have partitions, let's say, of 10,000 rows on each machine. Sort by will only sort the data within each partition of the data frame, but not overall, just within a partition. So it's highly efficient, and it can be done in parallel. You don't need to shuffle anything. You just sort within the machine, within the task. All right. Distribute by is used to kind of force a partition. It means that you specify what you want to organize your data by, for example, by country, and it's going to do a big shuffling over the cluster to make sure that all the data that corresponds to the same country lands on the same machine. Germany will be here, Switzerland will be there, China will be there, US will be there, and so on and so on. So distribute by is in order to do that. Now, if you both want to distribute your data by country, meaning that all the countries are on the same machine, and within the same partition, sort by country, turns out that there is a shortcut called cluster by. So cluster by is just a shortcut for sort by and distribute by at the same time, right? So cluster by is slightly less powerful than order by because it will, partition the data in the cluster. It will sort within the partitions. What's missing with cluster by is that your data is not overall sorted. There is no global order of your data. That's the difference between cluster by and order by. So order by would really make sure that there is an absolute sort of your entire data set all across the cluster and across your partitions, right? Is that clear? The difference between order by, sort by, distribute by, and cluster by. Any questions on that? All right. Now, as you can imagine, sort by, distribute by, and cluster by are a bit on a lower level because they kind of make you aware that there is a cluster and that there are partitions, so it can be useful to fine-tune the performance of your query. But the real high-level thing is still the SQL order by that here doesn't expose the partitions to the user. All right. So you can see here that there's going to be narrow transformations and there's going to be wide transformations. Where is a narrow transformation? It's just a filtering. So this is narrow, but the group by will need a shuffle because when you group by, you need to make sure that the same countries land on the same machines, right? So there is a big shuffle there. Then halving is again a narrow transformation because it's just it filters some of the groups out. And order by again needs to shuffle because you need to make sure to reorder the data globally over the cluster. So you see, if you have this whole sequence like select from where, group by, halving, order by, limit, and so on, you need one shuffle here and one shuffle there. All right? Okay. And one thing that I wanted to come back to, because one of you asked actually, it's the difference between data frames and relational tables. So typically in a relational table, we are in the first normal form. And that means that the values are atomic. So you have strings, integers, dates, and so on, but it's just atomic values in every cell. The difference that we noticed when we introduced data frames a few weeks ago is that in a data frame, you can also have arrays and objects, also called structs. So you can also have these new types. It means that it's not in the first normal form. This is an example. Here, I have a data frame where I have first that is a string, last that is a string, and countries that is made of arrays of strings, right? So here, I directly wrote the arrays here just because it was more convenient to create and more visual. I could also have drawn it with these vertical bars like in the style that I did a few weeks ago, right? That's also another way that I could have built the visual for the arrays of strings, right? But here I just conveniently use the JSON notation. Is there a question?
For last slide, doesn't the count operation need to take data over all compute nodes, which requires a shuffle to collect all of them?
So count star is for each group. So it's you count the number of items in each group. So it means that once you have shuffled and you already have all the rows that correspond to the same country together, if you need to count the number of rows in a group, they will all be on the same machine. Right? So this is the reason why you can just do it in parallel on the cluster. Right?
Yeah.
Thank you for asking. It's always good to ask questions. All right. Okay. So here we have a data frame with arrays of strings. And again, I use JSON because it's just more convenient. Well, it turns out that Spark extends SQL to be able to also manipulate arrays. And the way it does that is with a function that's called explode. What this function does is that it's going to create a row for each one of the values in there. You see like D, I, CH, and so it's creating a row every time. And what's going to happen is that the other rows get duplicated. You see, so there was Einstein in there. It just gets duplicated for every value that came from your array. Then you have Ramanujan here, Srinivasa Ramanujan with India and UK. And here you have Ramanujan twice. It's duplicated. It was here only once, but now it's twice there. India, UK, and so on, Gödel and Euler. So you see, this explode function transforms this data frame into that data frame. So you see that it's kind of a normalization, right? Because here it wasn't in the first normal form because there is an array here. And now it turns it into the first normal form at the cost of duplication. Now there is duplicates in the values in there. So this is one thing you can do with Spark SQL, with arrays. With 2 levels, you can also, so another way to do that, you can see it's quite involved, it's to create a lateral view where you kind of create, a separate view with the countries that you then explode and then put in there. And then you can have several lateral views and several levels. Imagine that now I have continents that have arrays of structs, meaning that I have a continent that here Europe and then a list of countries. So you see now even more nestedness that I represented as JSON. Now you can have a first level of explosion right there where you have the continents, and then a second level with the countries right there. And this is done with lateral view and explode. The first thing you might notice is that it looks complex. And you would be right about that. It's that really here we are pushing SQL to the limits of what it can do, because SQL was never designed to do that sort of things. SQL was designed to manipulate tables in normal form. So here you see that SQL becomes very, very complex. And in fact, that's the reason why in 2 weeks, we are going to investigate other ways and more appropriate languages to actually manipulate data like that, that is going to be more convenient than SQL for doing that sort of things. But nevertheless, I wanted to show you that Spark SQL has that. Even though it's complex, you can manipulate arrays like this and transform the data in that way. The same goes for objects. You might have here objects, a column that has objects like here that I represent as JSON. And here we can do select name dot first. So you see I can go inside and navigate inside the object and then promote these nested values here to actual columns. You see? So this is what happens with the dots. So lateral views for arrays and dots for objects give you a way in Spark SQL to manipulate data frames that have nested values, nested arrays and nested objects. Now, to finish that part, this is what happens if the data you're trying to parse doesn't fit in a schema and you really need to hit it with a hammer. And that happens. Imagine that this is your JSON data. So you see something's going on here, because here we have integers, but here we have an array. And of course, it's in JSON, that's fine, right? Because we don't have any normal form to respect, right? So you can absolutely have your data lying like that. And in real life, that happens. In real life, you will find data sets that have this issue. Now, what's going to happen with Spark if you try to parse it as JSON? We're using this spark.json.read that we saw earlier. Well, it needs to have a data frame. It needs to create a data frame out of that. But how can it create a data frame if there's integers and arrays? Well, the answer is simple. It hits it with a hammer, makes it a string, and turns everything into a string. So we have the string 1, the string 2, the string square bracket 3, comma, space 4, square bracket. You see, this is really a string. So you see, even though the data here, the JSON data, is not valid, there is no schema to infer, and there is no validity. So we saw a few weeks ago that you cannot turn it into a data frame. Well, yes, you can. If you hit it hard enough with a hammer, you can force it to fit in a data frame, but the cost of that is to put everything into a string right there. Is that great? No, because now you're basically telling the developer or the data scientist who is going to write Spark SQL on that, you're basically telling them, okay, deal with it. The string here is your problem, deal with it. That's very bad. That's very bad because now, imagine that you have now to process that in Spark SQL and differentiate on whether that's an integer or an array. That's an additional burden that you get. And that's not going to be easy to deal with. So this is another limit of Spark SQL and using SQL with that sort of data, is that it becomes quite complex. So again, the first limit is that with nestedness, the queries can get quite complex. And the second limit is that with heterogeneity, and you hit it with a hammer, you're making it much more complex to query and to do something with it with SQL. Okay. And finally, I think it's the last slide of Spark. You can also go back and forth between Sparks and RDD. So if you have an RDD, you can magically turn it into, if you have a data frame, you can magically turn it into an RDD. And if you have an RDD, you can magically turn it into a data frame. Of course, it's easier in one direction than in the other, right? If it's a data frame, then it's trivial to turn it into an RDD of rows. But if you have an RDD, it's not so easy to turn it into a data frame because you need a schema, right? If the RDD is too messy, then that will not work. So you need to provide a schema, and Spark is going to create the data frame according to your schema or throw an error if the data is not valid against the schema, all right? So this actually ends the part on Spark. Is there any questions? Anything that is unclear? Anything that you would like me to come back to or explain in more details?
So before reading a JSON into a data frame, one should validate the JSON first so that we don't get strings as in the previous example.
Yes, absolutely. If you want to turn JSON into a data frame, you need a schema. In order to get that schema, either you as the user provide it, so you basically tell the system what is your schema. This is what we did with JSON a few weeks ago. So you bring the schema as the user, or you want to go the lazy way and say, okay, Spark, please figure out the schema. I don't know what the schema is, please figure it out. And Spark will do it. So Spark will try to infer a schema. But the problem, again, with trying to infer a schema is that you might to hit with a hammer if it doesn't fit. So you might to go brute force with it. And so this is, did I answer your question in that way?
Sparse SQL tries yes, but then gives strings.
Yes, absolutely. That's exactly what happens. So these are the limits. So if your data is messy and you try to validate it like that, it will produce this very undesirable behavior that you basically create a schema that has a string there, and it basically pushed everything like the serialization as a string of the JSON content. And it will basically work, but it's going to be very, very, very cumbersome to actually deal with. So what do we conclude? What is the conclusion of that? It means that if this is your data, then Spark data frames and Spark SQL is not what you should be using. That's basically what it tells us. You can, if you want, force it and use it. It's going to be very hard. And we will see in 2 weeks that there are more appropriate languages and more appropriate tools when your data frames are nested or when there is heterogeneity. Does that make sense?
Yes. Thanks.
Awesome. Perfect. Yeah. So I take it step by step, right? So I'm basically doing this tour of the ecosystem, showing it like this works if the data is structured, this works if there is no nestedness, here it's more complex and so on. And then at the end of the lecture, you will have all of these technologies. And then depending on your data, you can pick what is the best. So if you have a semester project and you realize that you have data that is perfectly structured, that has a clear schema and so on, go for SQL, go for Spark SQL, go for data frames and so on. If your data is very small, then you shouldn't be using Spark, you should be using PostgreSQL, right? If your data is nested and heterogeneous, then there are other technologies indeed and so on. There is no technology that is perfect and solves everything. Every time for every project, you need to carefully look at your data. How big is it? What shape does it have? Is it in normal form? Is there a schema and so on and so on? And then you make your decision about what the technology is that you should be using, both for productivity and for performance. All right. Any other questions? Does it mean that everything was clear? That they explained it well enough that you understood everything I've been telling you? All right, so no questions. Okay, so let me then stop with this part, and then I'll stop the recording and come back to you with the next part on large scales. All right, so see you on the other side.